In this lesson on liquids and solids, we're going to take a look at solid structures, and we're going to take a look at the different cubic unit cells: simple cubic, body-centered cubic, face-centered cubic. We'll look at close packing of spheres, hexagonal close packing, cubic close packing. We'll finally finish this off with a discussion of the different types of molecular solids and some real small generalizations we can make about those different types of solids. And as always, if you learned something from this video, like it, share it, and subscribe if you'd like to be notified when I release more of these. All right, before we start talking about some of our ordered solid state structures, I just want to mention real quickly so that one type of solid is called an amorphous solid, and this is one that does not adopt any kind of crystalline, highly ordered structure whatsoever. And so glass is a really common example of an amorphous solid. The atoms or molecules are just all kind of trapped wherever they are, wherever they lie when it freezes or crystallizes, so to speak. I guess we can't really use the word crystallize because it doesn't form crystals in the same sense that these do. So now that I've got that little term out of the way, we want to talk about cubic unit cells. And there's three major types of cubic unit cells. There's the simple cubic, the body-centered cubic, and the face-centered cubic. And definitely need to know a few things about all of these. Now, to be a cubic unit cell, you have to have, to have a cubic unit cell, you have to have atoms at all the corners of a cubic-shaped unit cell. And that's going to be true for the simple cubic, the body-centered cubic, and the face-centered cubic. And I've got them all kind of drawn out in blue here. You will always have atoms in those three locations for all three of these. Now, if you're simple cubic, also called primitive cubic, that's the only places you have atoms located. And if you're body-centered cubic, in addition to the corners, you also have one right at the center of the entire cube. We call that the body center position. And if you're face-centered cubic, in addition again to the corners, the 8 corners of a cube, you also have them at the 6 face-center positions. So the top face, the bottom face, the left face, the right face, the front face, and then the back face, which is a little hard for me to draw. And you guys have been limited by my artistic ability a little bit in this lesson. So you should definitely know where all the atoms go in these three things, but then you should also know a few other properties regarding these. So, and one of them is called occupancy. So you want to know how many atoms are in each unit cell, and that's not as easy as it might look here. So, because if you look at this corner, and you look at this, and you're like, well, there's eight of them, Chad, in that unit cell, duh. Well, not exactly, because this corner right here is shared by 8 other unit cells. So think of having, this is a box right here, and you could have another box out front of it, and one over here, and one in the back. And so there are 4 different boxes that share that as a top corner. But then there's another level of unit cells above it that all share that corner as well. And so that atom that's at that corner, only 1/8 of it is actually in our unit cell. And the other 1/8 are all spread out among the other 7 unit cells that all share this corner. And so as a result, the occupancy here would be 8 corners times 1/8 of an atom per corner would be 1. And so our occupancy here is going to be 1 atom per unit cell. Now, if we go look at the body-centered cubic, in addition to those corners, we have one right at the very center of the unit cell at that body-center position. And that's not shared by any other unit cells. It's smack dab in the center. It's completely in this unit cell. And so that adds an additional atom. And so now we have 2 atoms per unit cell. And we move on to face-centered cubic. So in addition again to the corners, which supply us 1 atom per unit cell, we've got the face centers. And like if we look at this top face is shared not only by this unit cell, but the one right above it in the crystalline structure. And so that face center, half that atom is in the lower unit cell and half of it's in the upper unit cell. And so every single face center contributes half an atom. And there's 6 faces: top, bottom, left, right, front, back. And 6 times a half is an additional 3 atoms plus the 1 at the corners for a total of an occupancy of 4 atoms per unit cell. Next thing we need to talk about with regard to unit cells is what we call the coordination number. And the coordination number deals with how many nearest neighbors every atom in the structure has. So if we look at like in the simple cubic here, so let's say we take a look at this atom right here. His nearest neighbors are this guy, and this guy, and this guy, those 3. But also we have another one above him, another one out this way, and another one out this way as well. And so he's got 6 nearest neighbors. And so we'd say that his coordination number is 6. Now, if we look at the body-centered cubic, and this one's a little bit easier to see, and again, it doesn't actually matter if you look at the corner positions or the body-centered, it would work out the same, but it's easiest to see for that body-center because he is equidistant from all 4 up here and all 4 down here, and he's got 8 nearest neighbors, and so the coordination number is 8. All right, finally, the face-centered cubic one is the biggest pain in the butt to see. So, and you can look at it for the corners, you can look at it for the face centers, and neither one is particularly easy, especially with my artwork. So it's going to be a little pain in the butt here. So, but the way this works is, like, if we look at this face center right here, you can see his 4 nearest neighbors on those 4 corners. So, however, he's also, turns out, touching the 4 face centers on the sides all around the cube as well in this unit cell, and also the same 4 or analogous 4 in the unit cell, the face center positions on the one on the unit cell right above this one. And so he's got these 4 corners, these 4 face centers, and then the 4 face centers and the one above it for a grand total of 12. So, and like I said, you might be limited by my artwork here, but at the end of the day, if you memorize that the coordination number is 12, you're doing well. Cool. You could have also looked at it for any one of the corner positions and you would have determined ultimately the same thing. And again, it's a little more difficult and challenging here, 1, because it's a big number. So, but 2, it really would have helped if you saw this one unit cell in the context of a bunch of unit cells, especially like with a 3-dimensional model or something. It'd be much easier to see, but maybe take my word for it if you couldn't see that, or find a better picture. All right, next thing I want to see is a relationship here. So it turns out that we call the length of the unit cell A in every single one of these cases. So that's the edge length. We often define it as A. Some people would say S, but we're going to say A here. So, but then there's also the radius of an atom here, which we'll call R. And for each one of these unit cells, you might have to derive the relationship between the edge length and the radius. And that's often helpful in determining what we call the packing efficiency. So if we kind of look at it here, so my drawing sucks, just so you know, first of all, but these 2 atoms are actually in contact with each other. And so this edge length, they don't look like they're in contact, but they really should be. So the edge length here would go radius of one atom plus the radius of another atom. And so you have a very simple relationship here that just A equals 2R. And that is the easiest one to see. Okay, the hardest one to see is the relationship for the body-centered cubic, so we're going to deal with it last. So, but the next one we'll look at here is the face-centered cubic. And if it turns out where you're trying to figure out, well, where are the atoms touching? So it turns out they're touching right across the diagonal. So let's try a different color here, but right across the diagonal of one of the faces. So, and right across the diagonal of one of the faces, you'll have the radius of this corner atom, the entire diameter of the face center atom, and then another radius of the other corner atom. So that's a radius, a diameter, another radius, which is really just 4 radiuses, and that's the diagonal across. And so notice this edge length here again is A, this edge length is A, and if you work it out Pythagorean theorem here, you'd find out that that diagonal is actually equal to the square root of 2A. And so your relationship here is going to be square root of 2A equals 4R. And whether you want to solve for this and get a relationship, solve for A and get a relationship with R, or solve for R to get the relationship to A, it doesn't really matter. Either one's effective, but I think it's easiest just to see that that diagonal length right there, square root of 2A, is equal to 4 radiuses, and just leave it right there. Now the body-centered cubic is going to be the hardest one to see. And it's going to be hard to see, especially on my diagram here and stuff like this, because where the atoms are actually in contact is from one corner through the body diagonal all the way to the opposite corner up here. And so we're going to start here. Let's see, what's the easiest way to do this? Maybe do it starting here and make it all the way back corner, the exact opposite back corner, right through there. And this is going to be hard to see, especially because it doesn't look like I went through the body center, but I did. I'm supposed to. So you've got the radius of this corner, the 2 radiuses, i.e. the diameter of the body center, and then the radius of this guy. That's where the atoms actually touch solid. They don't actually touch. So 2 adjacent here, they don't look like they're touching, and they're not. Again, here they were. So in this case, then, it's that body diagonal, and that body diagonal is going to be hard to see. So what we're going to do is draw this triangle right here with a right angle right there. So let's draw that triangle. We'll pull it out. And so in this case, this is the edge length, again, just simply A here. This is the diagonal across one of the faces, which we just a second ago learned is the square root of 2A. And if you work that out, then Pythagorean theorem, A squared plus B squared equals C squared, this comes out to equal the square root of 3A. So, and that square root of 3A right across the body diagonal, again, comprised of 4 radiuses. And so we get our last relationship here, square root of 3A equals 4R. Cool. Now, each one of these you could use to determine what we call the packing efficiency. So in the packing efficiency of just a measure of the entire volume of the cube, what fraction of that volume is actually atoms relative to empty space? So like in the terms of simple cubic here, you got to know that the volume of a cube is side length cubed. So in this case, a cubed. And so packing efficiency is always going to be over a cubed. So in the simple cubic, you have a total of, again, an occupancy of 1 atom per unit cell. Well, you're supposed to know that atoms are spherical, and the volume of a sphere is 4/3 pi r cubed. And so here we'd have 4/3 pi r cubed over a cubed times 100. And that would be our formula for the simple cubic. And we just have to take into account that a equals 2r. And so we could replace a with 2r, or we could replace r with 1/2 a. So to make this work out and have the a's or the r's cancel and stuff like that, but the math would work out great. It would be similar here with the body-centered cubic, except now we have 2 atoms per unit cell. And so the volume of the atoms wouldn't be just 1 sphere, it would be 2 spheres. So, and now also our relationship between A and R is different. And again, we could solve for A and substitute it in right there and get the R's to cancel, or we could solve for R and substitute it right in there and get the A's to cancel. Either way though, we could calculate a packing efficiency. And finally, we'd get a similar equation if we did this for the face-centered cubic, but instead we have 4 atoms per unit cell. And so the volume of the atoms would be 4 times 4/3 pi r cubed divided by the entire volume of the unit cell. And once again, we'd have now an even different relationship between A and R and have to make a substitution one for the other to get this to work out. But when you actually take the time to do this, so if you got your study guide in front of you, you can see that you go from 52% here, packing efficiency, to 68% for the body-centered cubic, up to a maximum here of 74% for the face-centered cubic. So, and you don't have to know those numbers, but you should have in your mind though that the face-centered cubic has the greatest packing efficiency, has the least amount of empty space inside. That's something worth memorizing, but the numbers themselves, not super important. All right, now we've got to spend a little bit of time talking about what's called the close packing of spheres, a couple other different solid state structures, and there's 2 types here, hexagonal close packed and cubic close packed, and they're all based on this kind of base structure. So you've got a layer of atoms here, and there's one in the center, and for all the same size spheres, you can fit exactly 6 right around it. So, and that would constitute a layer. So what you find though is that if you actually picture these as spheres and you lay it down flat, is there'd be small little indentations where you could fit another layer of atoms on top, and they would rest right into those little recesses to kind of maximize the space being used. And so if we look at kind of the next layer here, you've got your choice on where the next set of balls could like kind of rest in place and stuff like that. So if we take a look and say, maybe we rest one of the next layer right here. Well, because I've used that spot right there, that automatically rules out that I can't use that spot or that spot. So, but I can use this one and this one, it turns out. Just like so. Cool, and I could make another one of these 6 around this center atom or something like that along the way. So, but you get this other layer, and it turns out I didn't again yet get to use this hole right here, or this hole right here. So, or this hole right here, it turned out. So we didn't get to use those on this one. Now, I've got this first layer in black, the second layer in red, and again, we're limited by my artistic ability here. So, but if you just repeat the black layer over again, and maybe I should draw a few more of these on here just for the fun of it. So I get a full red layer on there. So, but if we just repeat the black layer in the next layer out further, so, and just right where the black ones are, put another set of black ones, and just have an alternating repeating pattern of 2 layers, that's what hexagonal close packed looks like. It's just alternating 2 layers. And if you turn this sideways, we like to just say it's A, B, A, B, A, B, where every other layer is in exactly the same relative lattice positions as 2 layers before it. All right. Cubic close packed, on the other hand, has an alternating set of 3 layers, because the ones we never used, notice that hole right there is not only a hole where it was for the black layers and we didn't use it, but it's also a hole in between these 3 red ones right here as well. And so this next layer has a choice. It can go back and repeat the holes where the black ones were, or it can use the holes we've never used here instead. Cool. And then I could have this third layer, so as well, and then go back and repeat the black layer, and then the red layer, and then the blue layer, and work this out further and further and further. And so here we'd have this repeating 3-layer, and we like to say A, B, and C repeating each other, and then again A, B, and C yet again. So something along those lines. We're again back over here with the hexagonal close packed. It's just A, and then B, and then A, and then B, and just the 2 repeating layers. And that's the big difference. Now, it turns out both these have really high packing efficiencies. They both have coordination numbers of 12. So, but the big thing that usually you might be expected to know is just the pattern. Is it a pattern of 2 repeating layers or a pattern of 3 repeating layers? All right, last thing, I just want to compare the 4 major types of solids. So many we've already talked about, a couple we want to specify a couple more things about. But there are molecular solids, network covalent solids, ionic solids, metallic solids, and your molecular and network covalent composed of all nonmetals, your ionic metals with nonmetals, and then metallic all metals. If you look at your molecular and network covalent, so by far, when you've got nonmetals, by far the vast majority are going to be molecular. And what holds a molecular solid together is just, intermolecular forces, hydrogen bonding, dipole-dipole forces, London dispersion forces, which are rather weak when you compare them to the strength of a covalent or ionic bond. So network covalent solids are held together by covalent bonds. Ionic compounds are held together by ionic bonds. And the vast majority of both the network covalent solids and the ionic compounds are solids at room temperature. So to melt them, you actually have to break bonds, and that's really difficult. And so at room temperature, you don't have enough energy to break those. So whereas most molecular compounds, we can find them in solid, liquid, and gaseous phases depending on size. But generally, if you're going to find something existing as a liquid or a gas at room temperature, it's probably going to end up being a molecular compound. There'll be a few exceptions, like we've got, mercury metal. So, and a couple of metals that are just above room temperature might melt and stuff like that. However, the vast majority, again, of compounds that are liquids or gases at room temp, they're molecular compounds because the forces holding them together are rather weak in comparison to the rest of these. Now, network covalent solids, there's just a couple examples here, and we covered that back in Chapter 8. So you got diamond, quartz, and maybe even they'll throw graphite, another form of pure carbon on there, and things of that sort, and they're held together by covalent bonds. So, and you might just know that diamond's crystal structure has all of the carbon atoms in a nice tetrahedral lattice. And suffice to say, you probably know as much as you need to know about the crystal structures of these network covalent compounds. Now, for ionic compounds, you can kind of run away with this if you want to. So, and if you go to a little more of an advanced inorganic class, you probably will. And you'll start talking about some of the different crystal structures and the zinc blende structure and the cesium chloride structure. And I'm not going to get into that here. So one thing we did talk about, though, back in Chapter 8 was melting points for these and how that correlated well with lattice energies. So, and that was dependent upon the charges of the ions and the size of the ions. And I'm not going to get into that here again. Just wanted to remind you of that. So, but we haven't talked much about metallic compounds. And back in Chapter 8, we talked about them really briefly and said this is kind of this sea of electrons model. And we've got these loosely held valence electrons that are kind of delocalized throughout the whole metal and things of that sort. So we didn't really say much more, but I do want to talk about their melting points for just a second. And so usually the melting is going to be a direct correlation, or really, I guess, an indirect correlation to how strong the bonds are. The stronger the bonds, the higher the melting point. So the weaker the bonds, so the lower the melting point. And so if we take a look at a typical periodic table, so it turns out the strength of the bonding is one related to size. And so as you go up a group, you get smaller atoms in that metal. And smaller atoms form shorter bonds, and shorter bonds are stronger bonds that are going to correspond to a higher melting point. And so generally, as you go up a group, you get an increase in melting point. Whereas like cesium metal here might melt in your hand. By the time you reach sodium up here, I think it's got a melting point somewhere around like 200 or 300 degrees Celsius or something like that. So definitely an increase in melting point as you go up. So the horizontal trend for metals, though, is a little bit strange. And it turns out if you look at the horizontal trends, it corresponds well with the number of electrons available for bonding. And, usually we think with valence bond theory that half-filled atomic orbitals can be used for bonding, but once you start pairing up the electrons, so those are not used in bonding. And so what you find is if you start from the far left here, you get an increase generally, a couple exceptions, but an increase in boiling point as you go left to right. until somewhere right around the middle of the transition metals. And when you get to the middle of the transition metals, you've got a half-filled d subshell, all those unpaired electrons, which could be used for bonding. But as you get past the halfway point, you start pairing up those electrons, and all of a sudden the melting points start going back down, corresponding to weaker bonding going on. So just kind of a weird thing. The middle of the transition metals, it increases towards that middle generally, a couple exceptions. But that's the reason why. It's just the number of electrons available for bonding is greatest at the middle of those transition metals. Cool. That's pretty much all I want to say about these different types of solids and how I want to embellish here just a little bit at the end. And again, if you found this video helpful, like, subscribe, you know the drill. So God bless.